We will be starting in a few minutes, so call your friends. Hello, everyone, and welcome to session 5 of the Summer of Robotics. Previously, we have focused on building a foundational mobile base. We constructed the physical UIDF, established the hardware interfaces, and integrated an array of sensors to gather the raw data. Today, we will be diving into SLAM and robotic manipulation. Before we begin, let's quickly recap what we did in the previous session. First, virtual sensors. We successfully equipped our robot with cameras, lidars, and IMUs to provide us with continuous streams of data. Second, precise positioning. We took the noisy data from our sensors and fused it through an extended Kalman filter to get a highly stabilized odometry estimate. And then artificial perception. We implemented computer vision nodes using OpenCV for color-based object tracking and YOLO V8 for bounding box detection, allowing the robot to classify objects in its field of view. So what's next? Our robot can detect a target in the camera frame, but the moment that target leaves the frame, the data is lost. The system lacks state persistence. It cannot remember the layout of the environment or compute the path between 2 points. It cannot interact physically with its environment. To achieve these, let's look at today's roadmap. First is SLAM. We will implement algorithms that simultaneously construct a grid around the map and track the robot's coordinate frame within that grid. Then we'll look at navigation, in which we'll configure the ROS2 Nav2 stack to compute the global paths and handle local obstacle avoidance. And step 3 is manipulation. We will utilize coordinate frames and kinematic solvers to physically retrieve objects in the form of robotic arms. So let's begin with SLAM, which stands for Simultaneous Localization and Mapping. It is the process that allows a bot to simultaneously build a map of an unknown environment and track its own position and orientation within that map. Uh, these two properties are dependent on each other because the robot must know the coordinates of the map in order to find its location. And in order to find its location, it must know where it is in the map. So SLAM algorithms utilize probabilistic frameworks to solve both of these problems simultaneously. So why do we need SLAM? Let's take the example of a cleaner bot. Without SLAM, it will have no spatial awareness. It will have no idea where it is in the room and will move about randomly. SLAM, however, the cleaning bot will be able to generate a persistent map, allowing the robot to transition from random wandering to deterministic planning. It allows the system to compute systematic trajectories and optimize power and time consumption. There are numerous SLAM algorithms, but each one of them has four main functionalities. The first is sensor inputs. The algorithm requires high-frequency spatial measurements, which are given by LiDAR, camera, or depth sensor data. Then is state estimation. Because sensor data contains noise, the robot cannot blindingly trust the readings. It uses filters like extended Kalman filters, particle filters, or graph optimization techniques to calculate a probability distribution of its current position based on the sensor input. One is map building. As the state estimate is refined, the algorithm projects the sensor readings into a global map. And the fourth functionality, which is critical to long-term stability, is loop closure. Loop closure is the process of recognizing a previously visited location and updating the internal map to reflect this realization. As the robot moves, the odometry frame can drift. So if it were to travel in a large circle, its internal tracking could suggest that it did not reach its starting position. So loop closure algorithms uh, confirm the current sensor data and matches it with historical data, after which it recalculates the entire trajectory in order to make it a single closed loop. So we can classify loop closure into two types: vision-based loop closure and LiDAR-based loop closure. Vision-based loop closure relies on feature abstraction algorithms like SIFT and ORB. These algorithms analyze camera frames to identify distinct key points in the environment. The system builds a database of these key points, and when the current key points match the historical ones, a loop closure is triggered. LiDAR-based loop closure relies on geometric scan matching. It takes the current point clouds and attempts to align it to historical scans. A common algorithm for this is ICP, which stands for Iterative Closest Point. It mathematically minimizes the distance between point pairs across two scans until the geometry aligns perfectly. So implementing these algorithms from scratch would take a large amount of time. For that, we will utilize an open source package called SLAM Toolbox. The SLAM Toolbox is highly optimized and and supports both mapping and localization. We can install it using the command sudo apt install ROS Jaji SLAM Toolbox. We will now be utilizing the SLAM Toolbox to map our environment. Mapping is the process of using the sensor data to build a digital floor plan of an unknown environment. So the SLAM Toolbox now needs to publish its map onto a coordinate frame. And our robot currently tracks its own movement using the odom frame. So one might assume that the map should be anchored to the odom frame, right? Well, spoiler alert, it does not. So the question is why? The reason is odometry suffers from drift. After some time, the map will start to drift and no longer be accurate. So if we were to attach the SLAM map to ODOM, the map would slowly rotate and warp. To solve this, the SLAM toolbox establishes a separate static global frame called map. The SLAM toolbox continuously publishes on this frame instead of ODO, allowing allowing the map to be consistent throughout the process. So consequently, we must update our trajectory server node to reference the map frame rather than the ODOM frame. We will also modularize our launch files by removing the RViz from the base spawn robot launch file, and we will invoke these functions through the SLAM launch files. Now let's see how to build the launch file for mapping. The first step is to import the necessary ROS2 launch modules and configure the file paths for our URDF modules. Then we declare the launch arguments These act as runtime parameters, allowing us to toggle features in the command line. Third step is to give the code the exact addresses to our YAML files, which contains the parameters for SLAM toolbox. The next step is to tell ROS to launch the RViz as well as the interactive marker server to facilitate manual uh, movement of the bot. 5 involves calling the SLAM toolbox and passing it in the configuration files. And in the last step, we bundle all the settings, files, and programs together into one package so that ROS can start them asynchronously. So now let's see a demo of mapping. So the red arrows show the interactive market list. As we control the interactive market list, the bot starts moving around the map. All the white dots represent LiDAR scans, black dots represent obstacles, and the gray dots represent unexplored areas. As the bot moves around, the LiDAR produces new scans, causing the white area to increase. So now that we have mapped the environment, we face a problem. This map is only active in the local memory of RViz. We cannot use this map in any other instance. So to make this map useful, our SLAM toolbox offers three features: saving maps, serializing maps, and deserializing maps. The save map feature generates a static representation of the map. It outputs a .pagam image file containing the pixel data and a .yaml configuration file detailing the map resolution and origin point. Um, this does not contain the trajectory data of the bot and hence cannot be loaded back into RViz. Serializing map preserves the entire state of the SLAM algorithm. It generates a .postgraph and a .data file, which contains the full history of nodes, edges, and raw laser scan, essentially preserving the mathematical graph in memory. Deserializing is the inverse operation of the serialization feature. It loads a previously serialized map back into the SLAM toolbox's active memory. It allows the system to resume mapping an incomplete environment across multiple sessions without losing any data. So now that we've successfully mapped our environment, we will now see how to determine our own position within that environment. Localization is the process of estimating the robot's pose, which is its position and orientation within the map. We will be covering two methods of localization. First one being AMCL, which is optimized for a pre-computed static map, and the second being SLAM Toolbox, which is best for mapping unknown environments. AMCL stands for Adaptive Monte Carlo Localization. It is a particle filter-based 2D localization algorithm. It sounds pretty complex, but it's actually much simpler. It calculates all possible poses of the bot as a set of particles. It then continuously takes sensor data and motion updates from the bot in order to eliminate incorrect guesses, ultimately converging on an accurate estimate of where the robot is in the map. So when we start the simulation, AMCL scatters thousands of particles across the map, and the system considers all these poses equally probable for the bot. But as the robot receives sensor updates, the filter evaluates the likelihood of each particle. It simulates what a LiDAR scan would look like from the position of each particle and compares it to the actual LiDAR scan received. And particles whose simulated scans contradict the actual data are then eliminated, while those that align survive. Over successive sensor updates, this process forces the particle cloud to converge into a dense cluster, yielding a highly accurate, high confidence pose estimate. So, in order to use AMCL in our system, we need to first install it from the nav2 stack. It can be done by using these commands: sudo apt install rosjazzy nav2 bringup and rosjazzy nav2 AMCL. So now let's create the launch file for AMCL. First step is loading the necessary ROS tools and telling the simulator where to find the 3D model. Then we can create on-off switches that we can uh, configure in our command line. Then we pass the absolute path of our pre-saved YAML path into the nav2 pipeline. We have to use a pre-saved map because AMCL only works on a previously serialized map. It does not work on a completely new map. In step 4, we tell Ross to start Arvis on the interactive driving marker. In step 5, we load the nav2 localization program and feed it our custom settings. And in step 6, we bundle all the programs and files together so that ROS2 can execute. Now let's look at the demo. So as we give a 2D pose estimate, the simulation creates a cloud of possible poses of the bot. It then converges it to the best possible estimate of the 2D pose which we gave, and the bot then consequently moves to that pose. So AMCL has a problem in that it is computationally complex and it requires a previously serialized map. Instead, SLAM Toolbox offers its own localization, which uses graph optimization. In graph optimization, the robot's trajectory is formulated as a pose graph. Every discrete state the robot assumes over time is a node, and the odometry measurements linking these states are the edges. These solid lines um, imply loop closures, with the ever between the loop being Eij and the probability that it is a loop being omega ij. So to understand how graph optimization works, we have to model the graph mathematically. So the motion can be modeled as a function of its previous pose, its current speed, and the time difference between the poses. For example, your accelerate bot, which is a differential drive bot, would have the following formula to represent its pose. And then it models sensors by uh, taking it as a function of the current pose and the landmark position. So, for example, we'll take a range bearing sensor, which basically tells the distance of the bot from a certain landmark and the angle to the landmark. It is the difference between these two models that the graph optimizes. So now that we're done with the first quarter of the session, let's take a short hydration break. If Any of you have questions, raise your hands. We will unmute you. Okay. So now that we have a robust map and accurate pose estimate, we can now implement navigation. Navigation is the process of computing and executing a trajectory from an initial pose to a target goal while avoiding obstacles. Complete navigation pipeline has four main components. First is knowing where the robot is, which is its localization. Second is knowing where it needs to go, which is the path planning. The third is planning a path. And fourth is moving along that path while avoiding obstacles. So, how will we make these paths? Well, for that, Ross's nav2 stack has got us covered. It is highly modular and allows us to sequence different recovery, planning, and control plugins. nav2 stack sets the path planning to two domains. The first is the global planner, which utilizes search algorithms like A star or RTT star across the map to find the shortest path to the goal. And the local planner mm, uh, updates the route in case of a sudden change in the environment. It tries to follow as close to the global path as it can, but makes momentary changes in case of sudden obstacles. As you can see in this diagram, the global planner is at the bottom and has set the most efficient path between A and B. However, some obstacles have come in the way. So the local planner has to make changes to the global path while still trying to follow it. So now comes the question, how do we get the optimized routes through the map? The answer is cost map. The cost map transforms the grid of the map into a continuous cost surface. Each of the cells gets an integer value from 0 to 255. Free spaces get a cost of 0, while obstacles get the lethal maximum of 255. The planning algorithms compute routes that minimize the cumulative sum of the cell costs. Prevent the robot from just planning paths that race against the walls. Cost maps also utilize an inflation layer. This layer decreases as we go with distance from the obstacle. As you can see in this graph, the cost decreases as the distance from the object increases. Higher cost cells lie in the inscribed region of the obstacles, while relatively lower cost cells rely in the circumscribed region. There is also a buffer zone between the obstacles and free space that makes the robot prefer paths that keep minimum clearance. Now let's construct our launch file for navigation. The first step is to load the necessary ROS tools, and then we'll create our on-off switches, which you can change in the command line. And step 3 involves giving the code the exact addresses for a file. Again, in this code, we have to give the path to a previously serialized map as this navigation stack works only on a knows when both the mapping and localization of the bot is known. And then in step 4, we tell Ross to start RViz and interactive market twist. In step 5, we configure the nav2 localization and navigation launch files. In step 6, we bundle all the arguments, programs, and the nav2 files into a single launch description object. So now let's look at a demo for navigation. We first have to give a 2D goalpost. That global planning then sets the most optimized path from the bot to the port, which is represented by the red line. As you can see, around the bot is also a cost map. This cost map shows how the cost of the cells in the map. So as the bot reaches towards the wall, it creates an inflation move layer around it. As you can see, these light blue colors imply a very high detail cost, and as it goes outwards, it becomes lower in cost. Hello. Now that we can move our bot using navigation, it is preferable to give multiple points to the bots to move through. For that, the SLAM toolbox lets us use waypoints. And for the demonstration on waypoints, it will be a live demo. Okay. So as you can see my screen, we will now be I'll now be showing you the live demo for how waypoints work in ROS2 nav2 stuff. So first, let me show the launch files. So we'll be looking at the navigation launch file. Opening it in VS Codium. This is the launch file which we used in the navigation. We can reuse the same launch file for also creating nodes, as it already contains the nav2 plugin for Argus. Now we have to get two terminals. I'll first export my Gazebo model so that the files know where to find it. Then I'll move into my workspace, build my packages, and then I'll source this workspace so I can find the packages. Now in the second terminal, I again have to go to my workspace and source this terminal. So let's launch this robot launch file in this terminal. Command is ROS2 launch, VME ROS2 navigation, spawn robot launch. So now after it loads everything, the gazebo window will open. So I'll wait for the gazebo window to completely finish loading. So now in my second terminal, I will run the command for Arviz, ROS to launch BME navigation, navigation dot launch. So this will now launch the Arviz window, which has the nav to stack implemented inside it. Um, yeah, it takes a bit of time. Okay, so let me fix my screen first. Okay. Okay. So now for the navigation, we could set a nav to goal and the robot would just start moving toward it. As you can see, it creates the path, it creates the cost map, and starts moving towards the goal. These green arrows around the bot show its future possible pole. So Argis does not just calculate the current position of the bot, it also calculates its future position. And those green arrows represents its future position. Now that it has reached the goalpost, we can start waypoints. So we have to click this button in the nav2 plugin. And after that, we have to set some goal, some waypoint goals. Sorry. After setting these goals, you have to click start waypoint following. And as we see, the bot starts moving towards the waypoints. So first it will move to this one, and then it will start moving towards this one. So now, while we could place our own waypoints, it is also useful to give it to give it to a node. So now we'll look at how we can give the robot waypoints to travel across by creating a custom Titan node. So let me quit Argos. Let me close the gazebo. Okay, so now all processes are closed. Now let's look at the Python script for um, making the waypoints. So so in this code, we first have to import this RLCYPy, which basically is the ROS connection with Python. And then we have to define waypoints. So this here is a sample waypoint to position 2, 1.5 on the map. One thing to note is that we first have to convert it to quaternions because ROS does not accept Euler angle values. From there, we have to take the x, y, z, and w coefficients of the quaternion, and then we append it to our waypoints array. Then we define a function called sendGoal. This basically sends our waypoints to Arvis so that the bot can start moving around. Then we define the function for goal response. This is just to check if the bot has accepted our waypoints or if there has been a problem and had to reject it. And then feedback callback. Feedback callback tells us if the bot is actually moving towards the waypoint in the terminal. And get result tells us if the final waypoint has been reached. So now let's try running this node so that we can see the bot move. For that, we'll also be requiring another terminal. So now move to your workspace, source the terminal. Okay, so in the first command, in the first terminal, we have to give the launch command for the robot to spawn. On robot.launch.py. This will open the gazebo window. As the gazebo window opens, let's type the command for Arvis, which is ROS2 launch. Navigation. Okay, so with this, Arvis will now start. Takes a bit of time to load. So the Arvis is successfully loaded. Now let's go to our third terminal, and we will give the command for starting the waypoints node. So ROS2 run, DME, ROS2 navigation, UI, follow waypoint. So after we give this command, if we wait for a bit, it will start outputting messages about the waypoint. And as you can see, the bot has planned the path towards the goal. So the bot seems to have lagged out. So I'll try to rerun the script again. So I'll run the Argus file again. Okay, so the bot is back on. So now let me try giving the command again. So now it's starting to work. As you can see, the bot has calculated the optimum path to reach the point, as well as started to generate the cost map around it. And in the terminal, because of the functions, it has been giving us feedback on what the the current state of the bot is. As you can see, it's navigating to waypoint 0. One single waypoint is not that helpful. So how do we add more waypoints to the bot? So it's we just need to append more quaternions to the waypoints array. So if we look back at the code, so if you look back at the code, the format of this is the base is just the same. So I'll just paste this again. I'll just rename this as waypoint 2. So in all these WP1 variables, I will set them as WP2. I'll change the coordinate to go back to the origin. So now what will happen is that first it will append this waypoint to the Argus. So the bot will start moving to the point 2, 1.5. After that, it will accept the second waypoint and the bot will start to move back towards the origin. So saving this file, let's try running it. Work on build. Source the terminal. Now that you've built it again, you have to source all the terminals. Okay. So now in this terminal, we'll again run the file to spawn gazebo. Okay. Now I'm starting Arvis. And my Arvis has not opened, so let's restart the process. Okay, so launching it again. So what we should see in running both the waypoints is that after you run the Python script, we will be able to see two waypoints on the map, and the bot will then move from the first waypoint to the second waypoint. Um, It seems that Arviz is not opening right now for me. The system is running too slow. So I'll just be showing a demo video on how this works rather than showing the multiple waypoints in live demo. So till now, the navigation that we've done have all been done within a map which has been previously serialized. But what happens if we don't know the map? We are in a completely unknown environment. For that, the SLAM toolbox offers online SLAM, which lets us navigate without knowing the complete environment. So now let's see the demo. So as we set our nav2 goal in a gray area, which means that that area has not been explored yet, our bot still calculates an optimal path to the point, as well as creates a cost map around it. And as the bot moves towards the point, it maps the unknown part and updates the global path based on the updated map. So, congratulations. We've integrated these subsystems into the bot, and it is now capable of autonomous spatial reasoning and locomotion. So, do you have any questions till now? Alright. So now let's shift our focus from SLAM navigation to manipulation. And to understand how manipulation works, we will be seeing how kinematic chains link up in robotic arms. So this is the first we need to build our robotic arm. And so this will be its anatomy. First, we have the base, then we have shoulder, then the upper arm, forearm, the wrist, the gripper base, and the left and right fingers. If we launch the file, we'll see that we don't have much to work with, just the base. However, from the previous sessions, you have learned about how to build URDF models. So I won't be going in depth on how the URDF of this model is built. I'll just scroll over what URDF and physical parameters I have used. So now with all of that, our arms now starts looking like an actual robotic arm. All that's missing is the gripper and the fingers. But before we do that, we first need to check if the links have all been successfully chained up. For that, we will use the RQT TF3 plugin. It ensures it lets us verify whether all the links are correctly connected to each other and whether they are correctly uh, broadcasting their transformation data between each other. So now let's start building the gripper. So first we'll be creating a fixed base, which is attached to the wrist, and then we'll define the physical and visual properties of the gripper to be a gray rectangle. And then for actuation, we will define the fingers. So for the fingers, we will create a prismatic joint and making it slide along the y-axis. We'll give it physical and visual properties. And we also will have to give it surface physics. One thing to observe is that we have given it extremely high coefficient of frictions. This is required so that the fingers can later on pick up objects. Now with that, we have successfully built the complete arm. And if you notice to the side, there's also a joint state publisher. So what is this? This GUI lets us manually control the joints of the arm in RViz. It provides an interface to send uh, messages to move the arm. So in RViz, if we slide the values, you can see that the arm moves accordingly. Uh, so now we move the wrist joint and the wrist angle also changes. And if we move the finger joints, the distance from the center increases. But we face a problem. If we were to check this in Gazebo, nothing works. Not a single one of these the sliders are actually broadcasting data. So how do we fix this? So the best way is to use the RQT graph because it lets us visualize node connections. So when we open the RQT graph, we can see the joint state is publishing to the robot state publisher and to the robot description, which moves the robot in RViz. And one more thing to note is that ROS Gazebo bridge is not connected. Why is that important? The ROS Gazebo bridge node, it translates the data between Gazebo and ROS. ROS cannot directly send data to Gazebo. It requires a bridge, which this node does. So without this node, nothing will pass through to Gazebo. So now we have to connect the nodes such that the joint states node is connected to ROS and Gazebo bridge. And now the RQT graph will look something like this, with the joint states node now connected to the ROS Gazebo bridge. And yet we face another problem. We cannot rely on Gazebo-specific plugins for real-world application because Gazebo does not exist in real world. So we need to create our own node that publishes to the ARM without any dependence on Gazebo. So as you can see, we created a joint state broadcaster node that is connected to the joint states nodes. So this will still move the ARM in Gazebo, but it is not dependent on on the ROS Gazebo bridge. And now, if we were to run the files, you'll see a new GUI pops up. And now changing this values on this GUI controls the Gazebo model. So now let's look at how we can manipulate objects in the simulation. The first method is by friction, and the second method is by using detachable joints. You remember from our UID of code for the fingers, we have given very high values of frictions. This is to ensure that the object just does not slide off. However, simulating friction for every object gets computationally expensive, especially in large maps with large amounts of objects. So we can use a different method called detachable joints. This one assumes that the object can be held properly by the arm. And so we'll just attach it directly using a fixed joint constraint. So in order to implement this, we need to create a magnet to the fingers. So we have to create a gazebo tag in which we create two topics, one for detaching and one for attaching. And then we have to create a communication bridge so that the gazebo simulator can understand the ROS2 commands. Now, if we were to open up RQT, we'll see that in the topics, we get two options, one for detaching and one for attaching. And depending on which we click, the object will be attached to detached to the grippers. And still we face another problem. The gripper is essentially blank. It does not know if it actually successfully picked up an object. So our solution to that will be integrating a contact sensor to provide real-time collision feedback. So we'll first equip the robot's left finger with a contact sensor. This contact sensor is always on and updates at the rate of 100 Hz. And then we have to create a bridge between Gazebo and ROS2 so that we can identify what the object's holding in the RPT. So now suppose our arm is holding up the red block. Then in the RQT, under the contact section, you'll find two collision IDs. The first collision ID is on the left finger, which is because we attached the sensor to the left finger. So this will always be the left finger. In collision 2, however, we can see that it's the red box, which is what the contact sensor is currently touching. Another thing which is useful to create is the tool center point of the gripper. So for that, we'll just add a small red cube at the center of the fingers, which has no collision tag. So first we'll define a fixed joint, which is attached to the wrist. And then we'll define the visual appearance as a tiny red box along with its inertial values, and we'll give it negligible physics so that it does not interfere with the arm grabbing object. And now after implementing that, our arm will look like this. That small red cube at the center is our tool as our end effector. So now that we can detect objects and grab them, we want to be able to see them. So for that, we will integrate the RGBD camera. So first we'll define a fixed joint for the gripper camera, and then we'll define its visual and physical properties, making sure that it has negligible physics. And now we'll give it a static transformation. What so using OpenCV and a camera in ROS has a problem. ROS and OpenCV uses different coordinate systems. ROS assumes that the x-axis is forward, while OpenCV will assume that the forward direction is the z-axis. So in order to fix this coordinate mismatch, we have to rotate the camera along the x and z directions. And then we'll configure the RGBD camera in Gazebo, giving its resolution, frame rate, and field of view. After we integrate all that, we can see that that our arm can now see the environment. So in the first image is the RGB image, and we can see the objects in front of us. And the second image is the depth image. The more white the pixel is, the closer it is to the camera. So now that we can see these objects, we should be able to know their coordinates with respect to the base frame. However, our RGBD camera currently only gives us two information. First is the depth of the object with respect to the camera, and the second is the position of the object in the lens. So in order to get the coordinates, we need to follow a certain pipeline. The first is object detection. We need to write a script to identify the object. For this example, we'll make it such that it identifies red objects. So we convert the BGR data to HSV color space. HSV stands for hue, saturation, and value. This is to mitigate the varying illumination conditions. We then calculate the center of the x coordinates and the y coordinates across the whole red image. So now that we've detected our object, we now need to convert the 2D pixels on the camera to the 3D space coordinate. So for that, we will use the pinhole model of a camera. So the cameras can be assumed to be the point source of light. So any object can be connected to it by a straight line. And we can also use the properties of similar triangles in order to find the 3D coordinate from its 2D pixel. So the direction for the ray can be found using these first set of formulas. One thing to note is that the ray z is 1, which is a normalizing factor. These values do not give the actual 3D coordinates uh, of the object. It just gives us the direction. In order to get the exact coordinates, we have to multiply it with the depth of the object. So the final formula will be multiplying everything with z. To integrate this, Ross gives us some convenient functions. First one we'll use is the latest depth image. This gives us the depth image from the camera at this pixel point. Then we can use the project pixel to 3D ray function. This converts the pixel point and uses these formulas which we have discussed before, the first set of formulas, to find the direction of the ray. Then the next step is to multiply the depth with each component of the ray to find the final coordinates of the point. Now, the last part of the pipeline is the TF transform. So the previous steps have given us the object's coordinates with respect to the camera. We now need to shift the coordinates to get it with respect to the base frame. And for that, we can use TF transformation. So TF transform consists of two operations. First one is translation, which means moving the origin. It is represented by the T matrix, with Tx and Ty, Tz being the translation vector along the link. And rotation is the second operation, and it is constructed by multiplying the rotations along the roll, pitch, and yaw. The TF transform combines those two operations into one single homogeneous matrix represented by H. And now any coordinate can be conveniently shifted by multiplying it with the homogeneous matrix. So how does Ross implement it? It works by going down the TF tree. It chains the homogeneous matrices from the base link to the final link in order to get a final homogeneous matrix. So for a robotic arm, it will first calculate the homogeneous matrix from the base to the shoulder, then from the shoulder to elbow, then from elbow to wrist, then from wrist to camera, and multiply them together. And to integrate this, ROS again offers very convenient formulas. The dot lookup transform function lets us calculate the whole homogeneous matrix from the starting point, which is the base link, to the final point, which is our gripper camera optically. And then the do transform point multiplies the homogeneous matrix we've obtained before with the camera with the 3D space coordinates of the point with respect to the camera. Now, when we run the Python script, we can see that after it takes its time to load, it starts outputting that the red object is found. It gives the depth and then also the X, Y, and Z coordinates of the object. Now that we can see the arm, we also want to be able to autonomously move it, not just give manual angles to the joint state publisher. For that, we have to use forward and inverse kinematics. But calculating forward and inverse kinematics by hand can get messy and can result in errors. So why do it when we can let the simulation do it for us? So for that, we'll be using MoveIt2. It is a ROS2 based framework for motion planning. It helps in inverse kinematics, path planning, collision checking, trajectory execution, and grasp planning. Before we can use MoveIt, we need to change our controller settings first. More specifically, we need to add a gripper controller. So our RQT graph will now look like this with a gripper controller node, publishing and subscribing. And if you were to check out the joint state publisher, we can see that there are two controllers, the gripper controller and the arm controller. So now let's move on to a live demo on how to use MoveIt. I'll open my local phone. I'll share my screen. Okay. So now, in order to run MoveIt, first we have to go to the terminal, and then we need to go to our workspace. Yeah. And first we have to build the packages, because then only can our MoveIt assistant find them. So I'll run colcon build, and then I'll source this terminal. Okay, so now we have to run the MoveIt assistant using the command ROS to run MoveIt setup assistant, MoveIt setup assistant. So now we get the MoveIt assistant wizard. So what we'll do is create a new MoveIt configuration package. Then we'll browse through our files. So we have to select our URDF files. In this case, this is the file, the Mogiarm Zacro. So I'll open this. And then I'll load this file. Okay. So as you can see, the file has successfully loaded into the MoveIt assistant. So now, next thing we have to do is enable self-collisions. This is to so after generating the collision matrix, we can see that it's all the links are here. This means that no links will be able to uh, go on top of another. So now we'll be planning group. And here we have to create our kinematic chains. So let's first create a chain for the arm, and the arm needs a kinematic solver. So I'll give the KDL kinematic solver, and then we need to add the kinematic chain. Our arm will be moving from the base link to the end effector. So click the base link, and that will be our base link, and our end effector will be our tip link. So save. So we have with our first group. Then you can add. Then you need to add a second group for the gripper. No need to give it a kinematic solver, and we'll have to give it a joint. So we'll give both of our fingers for the joint, left finger joint, right finger joint. Save. So this is now what our groups will look like. And now let's go to robot for this. So over here, we can select, we can give it some predetermined pose. So for example, let me just bend the arm, and I'll call it my default pose. Okay. So now we have to give it our end effector. So add end effector. I'll give the name as EE, and the parent link will have to be end effector link only. So save, and then we have to add our controllers to it. So we can just auto add to the ROS2 controllers and to the MoveIt controllers. So after that, we have to give our author information. I'll just fill up my name and LDAP ID. And then in configuration files, we need to give it the file in which it will save all this data. So I'll put it inside this folder, and mm, I'll give it a separate name for MoveIt config. Okay. So now we have to generate package. This warning does not matter that much. So now that we have generated the package, we can exit. Okay. So now let's look at what that did. So we'll go into Robocarn. You can see it has created a folder called MoveIt config, and inside the config, yeah. So we see that the config folder contains YAML files, which means that these contain parameters for our robotic arm. So let's look at the joint limits parameter. Okay, so this file determines the velocity limits and the max acceleration, max velocity for each of the joints. However, there are some problems currently. Uh, First of all, is that we have to give the acceleration limits true, otherwise it just won't be able to move. So to all these joints, we need to change these false to true. And then the next problem is that, again, max acceleration cannot be zero, otherwise it just won't move. So you have to change all these. So we just need to change all these zero values to, let's just give 3.14. This one also 3.14. Okay, so now last thing is that we cannot just give it an integer value because whenever Python or C++ takes this parameters, they'll be expecting a double value. And if we just give 4, then it will just be taken as an integer, which could result in a type mismatch. So wherever it's integer, we have to give it a dot zero in order to make it a double. So this is our YAML file for joint limit. Now we'll also check out the ROS2 controllers YAML. This YAML file contains all the information for our um, ROS2 controller. And the MoveIt controllers YAML file contains all the parameters for the MoveIt controller. So one thing which we have to add in the ROS2 controllers are to the joint. We need to add two parameters. First one is action NS, which will set to follow joint trajectory. And then we also have to make it true by default. And the same parameters have to also be given for the gripper controller. So now let's save this file. So now let's try running the MoveIt assistant. So first we have to build our packages. As you can see, this MoveIt config is also built. Now we'll source our terminal. And for this, we require 3 more terminals. So let's get them all started. First, navigate to the workspace, and then source the terminal. Okay. So now in the first terminal, we will have to launch our robotic arm. So ROS to launch, ROS to simple arm on robot dot launch dot py. And we'll also use one of those parameters that you can config to make sure Arvid does not launch with this launch command. So we can set Arvid equal to false. And as you see, only Gazebo will be opening up. Oh, so I forgot to give it the I forgot to give it the directory of my Gazebo files. So I first have to do that. Now we can run the command for Gazebo. Okay, so now let's zoom in onto our model. Okay. So now in the second terminal, You will launch the move it config, move it group launch file. Okay. Move group dot launch dot py. Okay, so now it says that we can start planning. So now let's open up Arviz, ROS to launch, begin, ROS to simple on with config, move it, Arviz dot launch dot py. This launch file will now open up Arviz with the Move It assistant connected to it. So yeah, as you can see, this blue orb around the gripper is what is the Move It assistant. We can move this blue orb to control the arm. But before we can do that, we just need to, yeah, over here, we just need to make the uh, time for both Gazebo and Arvis to be using simulation time. For that, time set class move move group use and time to to okay. So now that that's been connected, we now move this around. So as you can see, we can move this around freely. So if we were to move it around, say here, let's check Gazebo. Okay, so the file does not seem to be loading in properly. It's most probably taking too long to load in. Try restarting the Move It Planner and see if that works. So run the Move Group launch file. And I can now start planning. So now let's run the Arvis file. Okay. So now if we move this in blue ball, then if we press plan, so as you, as you can see, it moved to my default state. In the Movie Assistant, I had set it to default pose, so that is what it has moved to right now. Unfortunately, it doesn't seem that the it is letting me rotate it freely. It's taking too much time for it to do it. Timeout reached. So the aspect of Move It Assistant is for you to just be able to freely move this blue ball around and so be able to control the kinematics of the arm. So with that, it brings us to an end to the fifth session of SOR. I would like to thank you for attending the session. If you have any doubts, so feel free to ask. So in the next week, we'll be releasing the project for the Summer of Robotics. From there, you'll be having to choose which projects you want to work upon. And that will lead to advanced certification. We'll also be releasing the assignment for this session later on.